So now let's find the last point of flight cell, the last GCP, which is the GCP number 2. So I know that it is located in this side of the forest. So if I look here in the Metashape, I can see this feature in here, then it should be around here. So I can right click and add a random marker. Then I go into here in this point 1, right click, and then filter photos by marker. Let's see how it goes. Yep. So I found the remaining point. Now I'm gonna delete this last point, remove markers, and I am going to add in the correct marker location. So right click, add marker, and then rename it as GCP number 2. And then now right click the GCP number 2, filter photos by marker. So double checking, GCP2 is the correct name. I will go just check image by image to see if the GCP is automatically allocated in the correct position. Looks good. Good. Okay. But again, if the GCP was allocated somewhere off the GCP, can always drag it to the correct position. Okay, that's it. So we finished the allocation of the GCPs in the image. I'm gonna save the project. I'm going to reset filter. So, and here are in this photos pane, all the uploaded images are accessible. Sorry. And then here in the model for the sparse point cloud, we can see the markers or the GCPs that we just created. And then you can see here that one of the images is selected. So the next step in our handout, and after the GCP allocation, so this is what we just saw. And now name the marker with the same name. We did the same name as defined in the txt file containing GCP coordinates. Well, these are the following file, this file, which is called biggoodedit. So when we collect the GCP coordinates with the GNSS receiver, we name the GCPs as GCP1, GCP1, GCP2, GCP3, GCP4, and so on. For this reason, we gave those names before, like GCP1, 2, 3, because they match exactly with this txt file, which we are going to import now inside the Metashape. And then you can see that besides the points ID, this file contains the geographical coordinates of these points which we're surveying the British national grid. So with these coordinates, we are going to georeference the sparse point cloud from a local coordinate system to the British national grid coordinate system. Okay, so I'm going to bring in this txt file now. Just see. Import the txt file containing GCPs coordinates once all markers were placed and correctly renamed. Reference tab import. So we are going here to reference tab and import in one of these small icons. So I click import and I'm going to navigate where this txt file is located. Here it is. So it already recognized the coordinate system. It already recognized the easting and northing. Start importing at row number 2. Okay. It has your pitch and rotation. No, it doesn't have, but it doesn't matter. So columns 1 is label, 2 easting, 3 northing, E for altitude. That's correct. And then I click OK. So it will say that it can't find match for some of the points I did. Well, this is correct because we have the GCP's name, but we also have the coordinate of other things we surveyed that day, like the ASD measurements or the ground calibration targets as well. So it's asking to create a new marker. You say no to all. So now it's recognized correctly. So each of these GCPs then has its easting, northing, and altitude position, and it estimates the error. So here we have an estimated error still in pixels of 0.1. So let's see the next in the handout. Define the coordinate system, it's okay. Well, then now we are going to hit optimize cameras, which will then transform from local coordinate system to this geographical coordinate system. So let's find this small icon for optimization. Export, import, convert, optimize cameras. We're going to hit this button. And let's just double check. We are just using the suggested options. So I'm going just to hit OK. It might take a while now. So after such optimization, there might be necessary a new check cleaning of this sparse point cloud. So yeah, because, well, as I said, now it's going to transform to this geographical coordinate system, and then yes, some of the points, they might be wrongly allocated, or they might be unrealistic. We have to double check. Okay, we'll pause the video and come back when. So now the camera alignment has finished. So we have to check again whether any of the sparse point cloud has very obvious errors. Let's see. I don't think so. Let's see. No, I can't see any obvious ones. Can use this freeform selection. Some random. No, I don't think so. But yeah, anyway, if you find some obvious points, then you can always come here again, then hit delete, then delete this wrongly project points. Maybe this one, the ones right here. Okay, then once you are happy after image alignment, You can always save the project. And then let's go back using this navigation icon. And then now the point cloud is projected into a geographical coordinate system. In this tab called Ortho, we can actually hit this show base map, and then it will sit exactly more or less in the place, in this case in the big wood. Yes, here we can see where the GCPs are, and then we can see that the georeference was correct. You can enable and disable the photos as well. All right, so up to here, everything okay. Let's see the next step in the manual. So up to this point, the panchromatic images were used. Well, yeah, when I wrote this handout, so we opted for using the panchromatic, but as I said, if you have the reconstructed hyperspectral image, you can use it directly. So, and then, yeah, from now on, the reconstructed hyperspectral image should be used for the next and final steps, which is generating the orthomosaic. So basically here, I explain that I have, yes, created this point cloud and saved this project, and then I sent over to, in that time, sent over to Rachel. And then she opened up this file, but the Metashape would not recognize the paths, the image, or in other words, for example, now each of these images has a path, right? If you come here and right click and you ask to see show info, you can see the path. For example, now I can go there inside this file path and replace this file. For example, this case, I'm using the panchromatic ones, but for constructing the hyperspectral one, I needed hyperspectral image. So if for any reason the software does not find the path, I should always indicate where the path is. For example, right click and then change path. So if I click to all cameras, I can then indicate where these correct images are. So, but yeah, in this case, I want to do this. So here I'm explain how to do this. Yes, to indicate where the hyperspectral images are. Here we go. Change path. Select all cameras. Well, so, but yes, then assuming that these are the hyperspectral images. So yeah, everything is okay, and then we can go to the next step, which is actually build the dense point cloud. So now we go back to this main menu, the workflow, and then the next step is build the dense cloud. Let's see, check the options. Lowest and aggressive. So yeah, we can always so check these options, and then when I hit the button, it will start the processing. Then here, the higher this quality, so yeah, it will increase the time of processing. This is by a factor of 2. For example, if this takes 5 minutes, this will take, I think, 20, and this will take 100, and then so on. It will always multiply by a factor of 4 more or less. So yeah, and once you do this, you click OK. It will then generate the dense cloud. Yeah, this may take a while as well. So after generated points cloud, further cleaning of unrealistic points might be necessary. So as always, we should do the cleaning again. Just stop. Well, now to generate an example of dense point cloud reconstruction, I'm going to resize the region in order to have a smaller sample Y. So I can use this tool here, resize region. I will decrease the box size, hopefully. It's a bit tricky playing this. And I just want a small region, so I can iteratively use these tools. Okay, so yeah, maybe a little bit smaller. All right, so we have a smaller area now. And then, so any of these process that we are trying now, they are applied inside this box. So going into workflow, build dense cloud, we want lowest quality and aggressive filtering. So I'll hit OK. Well, now it will take some time. I will pause. After some attempts, I couldn't discover some error is happening with my Metashape. It's popping up this message. It didn't finish the reconstruction of the densification of the point cloud. I'll just leave like this. But yeah, you should be able to finish this step, which will result in a denser point cloud. So yeah, then again, because here so we have a new point cloud, a denser one, we should check again for unrealistic points and do the cleaning if necessary, and then save it again. And then the next step is reconstruct the 3D mesh. So again, we come here in this main menu, the workflow, build mesh. Well, here, if you were successful, then you would select the dense point cloud. So as it's appearing here, so you would select the dense cloud, and then this suggested parameters. So I'll just go ahead and use sparse point cloud instead. Surface type height field 2.5 5D, face count high, and then interpolation enabled. Okay. I'll pause. So next step is actually building the orthomosaic, and then we go again here in the workflow, and then now many of the options they are active. Then build orthomosaic. It should be relatively quick. So we are in the British National Grid Coordinate System surface. We surface mesh, and then blending mode is disabled. So in theory, this should select the nadir closest to the nadir position. And then all these other options, they are going to do some processing to acquire the digital number for the final pixel. Then we have been using this disabled option, which has no blending. So then let's see. No, we are not using enable home filling. Then we just leave the pixel size as it is. Let's see if there is surface mesh, blending mode disabled. Yeah, here this final pixel size of 1.7 centimeter is quite is too high. I don't think we need this kind of precision. We should actually investigate it, but probably it should be all right to set this to 5 centimeter. And then, yeah, that's it. We can hit OK. So yeah, now the creation of the orthomosaic is done. And well, now we can actually see what has happened. If we come back here in the workspace pane, we actually have then the orthomosaic product in here. If you can see it in here. I will disable this base map. Yeah, this is it. I also, yeah. So I don't want to see the camera's position. This is the orthomosaic created. See, this is only for the box I just created. So yeah, the orthomosaic should be similar to this one, but created based on the dense point cloud. Yeah, it looks all right. So, and then we also have the other products, the 3D model, the mesh we created, and if I was successful in create dense point cloud, it should appear in here as well. So is the size of the file and the respective spatial resolution, 5 centimeters per pixels. Actually remember, maybe when you use the whole file, it might suggest a spatial resolution of 6 centimeters. So maybe just leave it like that. Now, because I used a smaller box size, it suggested, it resulted in a different pixel size. So yeah, and then the last step is actually export the orthomosaic to a folder of my choice. So I go here in File, Export, Export orthomosaic, and then I'll choose the file type of my choice. So pixel size, I select 5 centimeters, but it can't be 6 as well. This is suggested. Let's see if I have any other parameter. No, I don't think so. just make sure it's the correct coordinate system. We might want to change the pixel size or even split. These are other characteristics. Diff compression, if we want. Let's see. And just leave like that, and then we can export to a place of your choice. So yeah, this is it. Now then it should be able to be open for any SIG software. Yeah, I think I covered most of it. And then also another point I forgot to mention earlier. Here after the camera alignment, here the camera optimization, you can see the accuracy of the georeferencing. In this case, it's better than 2 centimeters. So yeah, well, this is probably not that good, but what is really important to see if there is any big error. For example, I don't know if this we would have 10, 100 meters of errors. Yeah, then something would be wrong. But yeah, in this centimeter level accuracy, yeah, it should be all right. Yep, that's it.